You know, there's a huge push for lighter, more fuel-efficient cars. And the auto industry's favorite answer right now is aluminum. It's strong, it's light, but it turns out it's got a hidden flaw, a really serious one that can cause it to fail, suddenly and without warning, right at the weld. So let's get into it. I mean, think about it. This is the central mystery that's had engineers scratching their heads. You take this high-strength aluminum, you weld it together into what should be a rock-solid bond, and yet, if the conditions are just right, a crack can just appear from nowhere and start spreading. So what's the deal? And look, this isn't just some weird science experiment in a lab. The stakes here are incredibly high. These particular aluminum alloys, the 7000 series, are absolutely essential for building the next generation of cars. Figuring out this dangerous secret is a really big deal for safety.
All right, so to solve this mystery, we first have to really understand the problem itself. That brings us to our first section, aluminum's cracking problem.
The culprit actually has a name: stress corrosion cracking, or SCC for short. Now, the best way to think about this is like a perfect storm for metal. It's not just a simple break. It's a very specific kind of failure that only, and I mean only, happens when three very specific conditions all come together at the same time. So what are the ingredients for this perfect storm? Well, first, you need a vulnerable internal structure in the metal itself, a pre-existing weakness, you could say. Second, you need a corrosive environment. For a car, that's easy. Just think about driving on a road that's been salted in the winter. And third, you need physical stress, something pulling on that metal part. The key thing to remember is you need all three. Take away just one, and the whole thing doesn't happen. Okay, so now that we've defined the crime, the investigation can really begin. Let's move on to Section 2, where the researchers started closing in on a tiny microscopic suspect right at the scene of the crime, the weld itself. So what you're looking at here, under a microscope, is where the story gets really interesting. Researchers found this specific material. It's a compound they call the T-phase that was forming right along the edges of the weld. And this little guy became their #1 suspect. So why is this T-phase so bad? Well, to put it simply, it's much more eager to corrode than the aluminum around it. It forms this continuous connected network. It's like a system of tiny corrosion-prone veins that creates a perfect little highway for a crack to travel right through the material. A fatal flaw, right at the microscopic level. All right, they had their suspect, but in science, you have to prove it. So that brings us to Section 3, where they came up with two really clever experiments to prove, once and for all, that the T-phase was the villain. Their plan was simple but totally brilliant. They came up with two different strategies. Plan A was to figure out a way to make a weld where the T-phase couldn't even form, basically eliminate the suspect from the crime scene. Plan B was to make a normal weld, T-phase and all, but then bury it deep under the surface. Isolate the suspect so it couldn't cause any trouble. So how'd they do it? Well, for Plan A, they just switched to a different kind of welding wire, one that was full of silicon. That simple change in chemistry meant the T-phase never even got a chance to form. For Plan B, they did something really cool. They used a technique called friction stir processing on a regular weld to physically shove that T-phase network away from the surface. And this is what that process looks like. Friction stir processing, or FSP, uses this spinning tool that gets the metal hot and soft, kind of like clay, but without actually melting it. Honestly, the best way to picture it is like using a super high-speed industrial mixer to just stir the surface of the metal, pushing all that weak T-phase stuff down and burying it safely underground, away from the air. Okay, so the stage is set. They have their standard welds, their eliminated suspect welds, and their isolated suspect welds. They were all ready for the ultimate test. It was time for the moment of truth. Section 4. The verdict is in. To prove their theory, they had to recreate that perfect storm, on demand. So they took all the different weld samples, locked them into this machine that put them under constant stress, and then stuck the whole thing inside a chamber that just blasted them with a hot, salty fog. It's basically the worst possible day for a piece of metal. And boom, here are the results. And honestly, it could not be more night and day. The standard welds, the ones with the T-phase right there on the surface, they failed. And they failed fast, in less than 15 days. But both of the modified welds, the one without the T-phase and the one where it was buried, they lasted for over 50 days with zero cracking, absolutely none. So yeah, the experiment was a huge success. The verdict was in.
By either getting rid of the T phase or just hiding it from the salty air, they made the welds incredibly tough against this kind of failure. The microscopic suspect was officially 100% guilty.
And if you need to see it to believe it, this slide is the smoking gun. On the left, that's the standard weld after the test. Just look at that massive crack running right along the edge. Now look at the right. That's the weld made with the new filler wire. Same test, same stress, same horrible salty fog, but it's perfect, absolutely pristine.
So, case closed, right? We found the culprit, we found 2 ways to stop it, problem solved. Well, in the real world of science and engineering, it is almost never that simple. Which brings us to our final section, the real-world catch.
Because here is the twist. The researchers themselves point out a major problem with their first solution. This quote from the paper says it all. Yeah, that new welding wire stops the cracking, but you should not use it anywhere that you actually need a strong joint. And this graph shows you exactly why. That black line, that's the strength of the new crack-proof weld. But look how low it is. It's only about half as strong as the original weld, that red line at the top. So you've fixed one problem, the cracking, but you've created a totally new one. The weld is now super weak. Not good. And that leaves us in a classic engineering pickle. Solution 1, the new wire, is crack-resistant but way too weak. Solution 2, the fancy friction stir processing, gives you a weld that's both strong and crack-resistant, which is awesome. But it's a complicated, slow, expensive extra step that's really hard to do at a place like a car factory that's churning out thousands of parts a day. So where does that leave us? Well, we've solved the fundamental mystery. We know exactly why these welds crack. The T phase is the villain. But a practical, easy solution that works in the real world, that's still just out of reach. We've solved the why. The next massive challenge is figuring out the how. How do we apply this knowledge in a way that's strong, safe, and scalable? The science is there. The question is, can the engineering catch up?